Welcome back to AI.Code.Cast. Today, we're diving into a problem that's pretty interesting. It's calculating the average waiting time.
Yeah, it's one of those classic coding challenges. It seems simple at first, but once you get into it, it's actually pretty complex.
Okay, I like that. So, like, imagine we're at a busy restaurant. There's one chef and a bunch of hungry customers. All these customers, they come in at different times. Their orders take different times to cook. We need to figure out the average wait time for all the diners.
Exactly. And, it's not as simple as just adding everyone's wait times and dividing by the number of customers,
Yeah.
especially on like a busy night. You need something more efficient.
Right, we need to optimize it. So how about we start with like the most basic approach, the brute force approach.
Yeah, that's a good place to start. So in brute force, we calculate the wait time for each customer one by one. Then we add all those times up and divide by the total number of customers to find the average.
So what's the problem with that?
Well, imagine 100 customers. You go through each one, figure out their arrival time, how long their order takes, calculate each wait time. It's just not efficient with larger numbers.
So it's like manually checking everyone's tickets at a concert. Yeah, you can
Yeah.
do it, but it would take forever.
Exactly. The brute force approach doesn't scale well. The bigger the problem gets, the longer it takes to solve.
Okay, so brute force is out. What's a better way to do this? Give me a hint.
Think about how a chef works. They take an order, cook it, and when it's done, they move on to the next one.
So we simulate that.
Hmm.
Could we track when the chef is available to calculate wait times?
You're on the right track. We can use a variable, let's call it availably, to keep track of when the chef is free.
Okay, I think I get it. Availability starts at 0, meaning the chef is ready to go at the beginning.
Yeah.
Then for each customer, we check if the chef is free.
Yeah, exactly. If the chef is free, meaning the arrival time is greater than or equal to availability, the customer's wait time is just their cooking time.
What if the chef is busy?
Then the customer has to wait until the chef is free. So their wait time would be the difference between their arrival time and availability plus the cooking time.
And we update availability after each customer.
Exactly. This is called a single pass simulation because we're like simulating the whole restaurant workflow in one go.
Sounds much better than brute force. We're not constantly recalculating everything.
Yep, we're only storing a few key variables, so it's also memory efficient.
Okay, I get the logic. Can we see an example to see how this works?
Sure. Let's say we have 3 customers. So customer 1 arrives at time 1, and their order takes 2 minutes to cook. Customer 2 arrives at time 2, and their order takes 5 minutes. And lastly, customer 3 arrives at time 4, and their order takes 3 minutes.
Okay, got it. Let's see how this plays out.
All right, so availability is 0, meaning the chef is ready. Customer 1 arrives at time 1. The chef is free, so their wait time is just the cooking time, which is 2 minutes.
Okay, makes sense. So no one's waiting yet.
Yeah.
What happens to availability now?
We got to update it to show when the chef is free again. So it'll be 1, the arrival time, plus 2, the cooking time, which equals 3.
So availability is 3 now. What about customer 2 arriving at time 2?
Now it gets a bit tricky. Customer 2 arrives at time 2, but the chef's busy with customer 1's order until time 3. So customer 2 has to wait 1 minute.
Right, they got to wait for that first order to finish up.
Exactly. Then customer 2's order takes 5 minutes to cook, so their total wait time is 6 minutes. 1 minute waiting plus 5 minutes cooking.
And we update availability again, right?
You got it. We add the 5 minutes cooking time to the time the chef became available, time 3, making it 8. So availability is now 8.
Okay, on to customer 3 arriving at time 4. I'm guessing they'll have to wait a bit too.
Yeah, you're right. Customer 3 arrives while the chef is still working on customer 2's order, which won't be done till time 8. So customer 3 has to wait 4 minutes.
And then we add their cooking time of 3 minutes, giving them a total wait time of 7 minutes.
Exactly. And one last update for availability. We take the time the chef became available, time 8, add the 3 minutes cooking time, and we get 11.
Right, so customer 1 waited 2 minutes, customer 2 waited 6 minutes, and customer 3 waited 7 minutes. How do we get the average waiting time from that?
Just like any average, we add up all the individual wait times. 2 plus 6 plus 7 equals 15 minutes. Then we divide that by the number of customers, which is 3. That gives us an average waiting time of 5 minutes.
Pretty good for a busy night. And we did all that in one go, just like the chef going through the orders. But you said there are other ways to do this single pass simulation.
Yeah.
What else is there?
We could try tracking the chef's idle time.
Idle time? You mean when they're waiting for the next order? Why would we track that?
It might seem small, but tracking idle time gives us a more accurate picture. It lets us account for those little gaps in the chef's schedule.
Okay, I'm interested. Do we still use availability?
Oh yeah, availability is still important. And just like before, we compare each customer's arrival time with availability to see if the chef is free. If
Yeah.
they are, the wait time is just the cooking time, and we update availability. But there's an extra step if the customer arrives while the chef's busy.
Okay, what's the extra step?
We calculate the chef's idle time before the customer arrived. It's the difference between the current customer's arrival time and when the previous order was finished. Basically, how long the chef was waiting between those two orders.
So if customer 2 arrived at time 2 and customer one's order finished at time 3, the chef's idle time would be 1 minute.
Got it. What do we do with that?
We add it to the customer's total wait time. They're not just waiting for their food, they're also waiting for the chef to be free.
Ah, I see. It's like a penalty for coming in at a busy time. But won't this make the calculations more complicated?
A bit, yeah. But it gives us a much clearer view of how wait times are affected by when customers arrive and when orders are finished.
Like choosing between a regular picture and a high-definition one. Both show the same thing, but one has more detail.
Exactly. And just like with pictures, which one you pick depends on what you need. If you need to be really precise, then tracking idle time is better. So it's not just about finding one best solution. It's about knowing the pros and cons and picking the right one for the situation.
Yeah.
But before we get too deep into that, can we go through an example with this idle time thing?
Of course, we can use those same 3 customers.
All right, so we're back with our 3 customers. Customer 1 comes in at time 1. Their order takes 2 minutes. Customer 2 arrives at time 2. Their order takes 5 minutes. And customer 3 arrives at time 4 with a 3-minute order. Just to recap, how does tracking the idle time change things?
Well, it's not just about when the chef is free. It's also about those little gaps between orders when they're not doing anything. We want to see how that downtime affects the wait times.
Right, okay, so let's go through it step by step. Availability starts at narrow. Customer 1 comes in at time 1. No waiting 2 minutes to cook, so we update availability to 3. What happens next?
Okay, so customer 2 arrives at time 2, but remember, the chef's busy with customer 1's order till time 3. So first we got to figure out the idle time. The chef finished at time 3. Customer 2 arrived at time 2. So there's 1 minute of idle time.
Right, that little break where the chef might be getting ready for the next order. We add that 1 minute to customer 2's wait, then add the 5 minutes for their order. So
Yeah.
6 minutes total.
You got it. And
Yeah.
then we update availability again to show when the chef is free. It'll be time 3 when they became free, plus the 5 minutes cooking time, so 8.
Now for customer 3 coming in at time 4, the chef's still busy with customer 2's order, which won't be ready till time 8. So customer 3 has to wait 4 minutes. Do we add idle time for them too?
Good question. In this case, no, because customer 3 came in before the chef finished the last order. So their wait time is just those 4 minutes while the chef finishes up.
Makes sense.
Yeah.
So no extra idle time for customer 3. Just add their 3-minute cooking time to the 4 minutes of waiting.
Yeah.
So 7 minutes total. And we update availability at one last time to 11 after customer 3's order is done.
Yep, that's it. So we've got customer 1 waiting 2 minutes, customer 2 waiting 6 minutes, and customer 3 waiting 7 minutes.
The same as before. So adding the idle time didn't change the average wait time this time, but I can see how it could give us a more accurate picture if things were different.
Yeah, exactly. Both ways simulate the chef, but tracking idle time gives us more detail, which is sometimes important.
This has been a really interesting look at the average waiting time problem. It seems simple, but there's actually a lot to it. But by breaking it down step by step and using techniques like single-pass simulation, we can find some pretty cool solutions.
And the best part is these techniques can be used for all sorts of problems, not just restaurants. Anything with cues like traffic flow or even computer systems.
It's like we found a new way to understand the world around us. So to all our listeners out there, keep those minds sharp and never stop learning.
Thanks for joining us on AI.Code.Cast for this deep dive into the world of code